I'm very happy to be at the Field Institute with Professor Burris, and he's one of the few experts I know who has actually read all of Boole's original work on logic. And so maybe we could jump right in with asking you about your own work. Tell us a little bit about your own work.
I have been using Boolean algebra throughout my career. And about 20 years ago, after 30 years of working with Boolean algebras, I decided to go back to Boole's work and study it carefully. And I knew that it was a difficult book to read because I had looked at it as a young mathematician. And it looks easy, but it's actually very complicated to sort it out. And I wanted to do that. And I have been now looking at it for 20 years. And still finding nuggets to sort out.
How did Boolean algebra become incorporated in the area of your research?
Well, Boolean algebra was always a part of logic from the very beginning. One could say that logic started with Boolean algebra. And the algebra of Boole changed into Boolean algebra that we know today. But it was a main source of ideas about how to work with equations in the late 1800s. The very beginnings of equational logic are probably based on Boole's work and the people that followed in the 1800s. And my specialty was equational logic. And so it came in naturally. And then there were other questions that I was interested in, like decidability. And Boole had the original technique called elimination, which is used for proving decidability. And it was popular up through the 1950s and 60s, and probably still, to prove decidability results. And so I always wanted to go back and see exactly what Boole did on this elimination theorem to prove decidability. And I think I know now.
So what Boole actually did at his time, was it a leap?
Oh, Boole, it was like nothing else around. People didn't know what to make of it. The subject of logic of classes had belonged to philosophers. And there was this unpleasant dispute between De Morgan in London and a Scottish philosopher named Sir William Hamilton over a fight over the quantification of the predicate, meaning when you say all x is y, you could say all x is some y, or all x is all y. There you're quantifying the predicate y is y. And they got into a fight over priority over this little smidgen. It went on for, I think, 20 years. But it was this fight that got Boole thinking about logic. And within a few weeks, he had all the ideas for his first book. It was just amazingly quick. Nothing like what anybody else was doing to bring in equations. And then to go as far as he did. I mean, he didn't just have the basic ideas. He had a plan for what should be done with the subject. What were the goals? He laid them out. And by 1854, he had accomplished them. Amazing.
So how would you view Boole's impact on modern society?
Well, I think when we look at the influence of Boolean algebra in circuits and in automata and logic everywhere, it's hard to think of how modern society would function without Boolean algebra. Well, certainly his application, the application of his work to circuit theory is by far the best known, and that computer design. That I had a friend when I was a graduate student. A friend came back from working on computers for missiles back in the 1950s. That was, of course, the Cold War going on. And he had been in California, and he told me that although he wasn't himself involved in designing, but he was in a group that worked on these computer designs for missiles. And he said the only tool they used was Boolean algebra. So he came back to graduate school to do his PhD in Boolean algebra.
So Boole is sometimes mentioned as one of the founding fathers of information technology. What would be your view on that claim?
Well, I would be very happy to support that claim. I think that Boole's work in managing data by symbolic means is perfectly within information technology, one of the real founders.
Where would you place Boole in the broader context of your field?
Well, Boole was the one that got the ball rolling. He was the originator, the one who got the people thinking about symbolic logic, equational logic and such. So he was the real beginning. His work on the elimination theorem is the one that I regard as the most beautiful. Of course, people in other areas might be inclined to think his work on Boolean circuits, applications to Boolean circuits. But the elimination theorem, there was nothing else like it before that, and it was a theorem that people focused on, like Schroeder spent a good part of his 3 volumes, Algebra der Logik, looking at the elimination theorem, trying to generalize Boole's work. He did somewhat. And then Skolem later on in 1919 extended it even further. Tarski worked on it. So this result, I think is beautiful.
So is there an achievement that's perhaps buried in his work that he should be better known for?
Yes, well, in his book on logic in 1854, he, after giving some axioms for his system of algebra of logic, he suddenly made a transition without much fanfare, saying that, well, really, we ought to look at the numbers that are idempotent, namely 0 and 1, and look at the algebra of numbers where the variables can only take on the values 0 and 1. He says, if you look at that, he says, all of the axioms and laws and processes are exactly the same as in logic. This is my foundation principle for this work. End of what discussion. He gave no further reason for why it was a foundation. No one that I know of until a couple of years ago in my work with Sankapanavar even commented on this except to dismiss it. And yet he was absolutely right. It's a beautiful result. And it's very much like you can test an equation in Boolean algebras by looking at the 2-element Boolean algebra. It's very similar to that result, way before that result.
Yeah. Could you expand a bit more for people who are maybe not technical? I mean, most viewers will be more technical, but people might confuse it with thinking, well, Boole did work with zeros and ones. So what is the difference between the fact that he worked with zeros and ones and the 0-1 principle or rule that you mentioned?
Well, as you know, Boole's work has been difficult for people to understand. It took over 100 years before Halperin was able to show that a big part of it made sense. And I think the real reason was that people didn't believe Boole when he said that the algebra of logic was the same as the algebra of numbers except for the law x squared equal to x. So Boole was really looking at the laws of numbers, and he was depending very heavily on the algebra of the integers. So he was using 0, 1 in the integers, not as a 2-element Boolean algebra. That was the difference.
Could you hazard a guess at what Boole's contemporaries, or Boole himself for that matter, would have thought of the modern applications of his work?
Well, I think most of the modern applications were way beyond their imagination. Boole thought his work in logic would be useful when combined with his work in probability theory, because then one could take large sets of data about social conditions and sort through them with Boolean reasoning, his logic, and come up with statistical information on what happens in large populations, like deaths are well known in insurance business, mortality rates. And he thought there were other nuggets one would be able to find by using his algebra. And after him, Jevons, who did the first major modification of his work towards the modern version, was able to see that this could be mechanized. And he built a small piano-like machine that could answer, that could solve Boolean equations in 4 variables.
One way of reading it is might be that Boole laid what could be seen as early foundations for data analytics.
Oh, I think Boole would have been thrilled with computers, because he mentions that, well, he knew it would take a lot of effort, a lot of people working to do all of the computations, and but he thought, people, the government or whoever would have to decide if it was worth the cost. But I think he did think it was worth the cost.
Just thinking about what Boole has done and basic research as it stands right now, I just wondered what your views might be on basic research in general, and is it still relevant today?
Oh, I think it's absolutely relevant. I mean, you look at Boole's work, and it took 75 years or more before it really found its applications. And then there were sensational applications to computers and electric circuits. And of course, they became popular in modern logic, mathematical logic. So I think basic research is absolutely fundamental to society's progress.
Where would science or society be if Boole would not have been?
Well, of course, it's always difficult to project history, but I don't know of anyone else that was working on the ideas that Boole was working on. And at worst, it would have meant that the digital age would have been later in coming. We might still be doing a lot of things analog, and we might not have these little handy telephones that we use these days if we didn't have these developments.
So how long do you think Boolean algebra will be taught towards the future?
Okay, well, I think that Boolean algebra is absolutely fundamental to all of these applications to circuit theory and computers, and it's important in mathematical logic as well. So I see it almost as fundamental as numbers. I think it will be around forever.
How would you envisage Boole's work still affect future developments?
Well, there's so much that we don't know in the development, study of the genome, and the big push now to understand the brain. And I can imagine that Boole's work will be important in many of these future research projects.
So a question I had in mind was, when you read through the entirety of Boole's work, whether he would come out as a person, a mathematician, who had computation even more at heart than was priorly realized. Would that be accurate?
Oh, yes. Well, Boole made an emphasis of the fact that it was not only the development of a theory that was important, but it was important to have a sense of direction as to what to do to get to the answer. And he called this a method. And he developed a method to get what he thought would answer the most important questions in logic. That was his elimination theorem and his solution theorem. Both of those are algorithms. And that was his focus, was the algorithmic work.
Yeah, so he basically realized part of what Leibniz's dream was. Would that be a correct?
Oh yes, he was definitely thinking of making things algorithmic and wanted a procedure. You see, he was being attacked by the old-fashioned logicians because they thought their syllogisms were enough to do everything. His elimination theorem was a generalization of syllogisms, but they were claiming that if you stacked enough syllogisms together, you could get his results. And Boole pointed out that, well, but they haven't shown you how to stack them together. There was the missing sense of direction. And he emphasized the importance of direction to the success of a subject. And that would be the algorithm. It was everything in logic in those days, right? There was nothing else.
No.
And you can imagine Boole working all alone. I mean, he had to have almost everybody against him, and some of the early editorials, were, I think the editor of Mind, I guess, wrote an editorial on his book, saying that, well, one of the examples he did, here's how I would do it with syllogisms, just as short, and so, what's the point of Boole's work? Yeah. He's not contributing anything new. And before that, the only equations were for numbers, but now you had equations for classes, and what were the rules, and how did you work with them? So this was, so I think Boole started a good part of modern logic with this. certainly in my area, which was equational logic in the early days. And so I'm very grateful that he was there.
Yeah, it wasn't even easy for contemporaries who knew it, I imagine, to read it.
No, because they just, Boole did not have the vocabulary to explain things to them clearly, and they jumped into conclusions that were on the wrong track, which made it all the more mess to understand, and so you get a lot of negative comments all the way up, through 1950s and 60s, and it wasn't until Halpern came along that suddenly there was light with multisets. I wish there were a book out that gave a modern version of Boole's work in the simple language that Boole used. But that's not easy. I've thought about that a great deal, and it's altogether too easy to become very technical to explain things. And Boole's book looks easy to read. So if one only could come up with a modern version that was readable, I think it would sway opinion of what Boole had done. I wrote a book on logic for mathematics and computer science.
Right.
It came out around 96.
Online, yeah.
And in that, I did put in Boole's theorem, because I was so delighted with it, and I thought they really should know.
Mm-hmm.
And I remember lecturing on it the first time before the book was written, and I mentioned this was Boole's theorem, and one of the students, how do you prove that? So I wasn't planning to prove it, but I had to think quickly and come up with a proof for the student. And they were quite interested in this result. Yes. It seemed amazing. It was so simple.
Yeah. There must be links with rewriting as well. Rewriting.
Yes, exactly. And finding optimal ways of proceeding with equations. Boole was into that, with abbreviations, and he usually gave 2 or 3 methods for doing things. So
it must have been the tip of the iceberg as well. What he wrote, obviously his book is the tip of the iceberg, but all the computations he had behind it for checking the university.
I only wish he'd written a diary, because how did he come up with those ideas? We mentioned in our correspondence this idea of the basis that he chose for his polynomials, and it was amazing. Where did that come from? It works perfectly. And yet this was evidently something that he cooked up in the few weeks it took him to write his first book. And so there's so much amazing stuff in that book. That, if I only had a diary, I'm sure it would have been a bestseller. So he was, taking the things you do in algebra and moving them over to logic and how you reason. He was trying to show that your reasoning was governed by mathematics. You see, that argument with De Morgan and Hamilton had to do with, it got rather heated, and Hamilton, being a philosopher with no particular mathematical background, wrote some very nasty things about mathematicians, about how studying mathematics deprived you of all the natural understanding of beauty and such in life, and made you rigid and narrow, and that I think Boole's was coming to De Morgan's rescue when he wrote that book. Because one of the things he says in his first book is that now we see that logic no longer belongs to metaphysics, it's a part of mathematics. He wrote rather subtly, I think, because he was, after all, at that time he was just running a little private school, I should say. And he didn't have a degree in anything, and he was a nobody from the academic point of view. And yet, so so he was a little bit cautious about his words that he used. He tended to be rather gentle when he said things. But if you read carefully, I think you will see that what his point is. There were some shorter biographies, but nothing really, major. Like Hamilton had magnificent biographies written after his death, but not Boole. And if you look at Macfarlane's book on 10 British mathematicians in the 19th century, he hasn't one on Boole. So this is around 1916 this was published. Lectures from 1901 or 2 by Macfarlane. So he was saying in his book that when he was recently back in Europe, he talked to some of his friends as to why it was, this is around 1900, why it was that this biography of Boole had never been published. And they said the problem was his wife. Evidently, she had some demands that would have been very difficult for honest mathematicians to put in. I think, later on she became somewhat mystical. And that probably, that she saw hidden messages in Boole's work. And they probably weren't willing to go quite that far. And it ended up sort of torpedoing things, according to his article.
I wondered about the name Boolean algebra. Would you have a way to trace back when the term Boolean became attached to that concept?
It seems that it became firmly attached in around 1913. Charles Sanders Peirce, whose father had been a very famous prof at Harvard, gave some lectures in the late 1800s. Now, he occasionally used the word Boolean logic or such, but not consistently. Other people hardly use it at all. They would have maybe Boolean J. von Schroeder or some hyphenation. And then a philosophy prof at Harvard named Josiah Ross was halfway through his career when he heard a lecture by Charles Sanders Peirce around 1898 at Harvard on logic and reason. And he got terribly excited and decided to learn logic and mathematics and went into a crash course. And by 1913, we see a paper by one of his PhD students, Schaefer, and another by him, both using the word Boolean algebra. And it seems that the people at Harvard decided this was a good name. And over the subsequent years, it was used again and again until you get up to the 1930s, and Marshall Stone, who was a Harvard PhD and professor, wrote his two famous papers on Boolean algebra. And I think by that time, the base was there. There were, up to 1940, there were about 50 papers on Boolean algebra, and only 2 or 3 were published in foreign journals. So it seems to have been this Harvard clique, along with one stray mathematician named Bernstein at Berkeley, who wrote a lot of papers on axioms for Boolean algebras, 13 or 14, I think. And those two together, working together, seem to have solidified the name Boolean algebra. And nowadays, most people don't know where the name came. They assume that Boolean algebra was always the name, but that's not the case.
When Boole started his investigations, algebra was just emerging, if I'm right about this?
Well, the study of the foundations of algebra was just emerging. I mean, algebra had been used since 1000 AD, but it was in the 1500s that they started getting exciting work when they discovered they needed complex numbers to describe cube roots of polynomials, and polynomials of the third degree. And after that time, algebra was going through a tortured period where they developed, they had negative numbers and complex numbers. And even up in 1800, you had people who did not believe in negative numbers. For example, De Morgan's father-in-law wrote a book about how, on mathematics, he was a math graduate at Cambridge, and he wrote a book on how this hooey about negative numbers and complex numbers was nonsense. The positive numbers were the only things that were real.
So let me rephrase that. Maybe abstract algebra was emerging. Would that be a fair
abstract
statement?
algebra, yes, because it was only in this time they were beginning to look at different interpretations of the algebraic symbols. It started probably with George Peacock, who wrote a book in 1930 in which he decided to explain the imaginary numbers by doing away with them. He said there were 2 kinds of algebras. There was the algebra of positive numbers. This was real algebra. And then there was just this symbolic stuff that you did, and you had square root of -1, but it didn't mean anything. The thing was, as long as you followed the rules, the end result was going to be okay, even if it went back into positive numbers at the end. And this was the beginning of 2 interpretations, or the symbolic and in one hand, and then the limited interpretation in the positive numbers. And when Boole came along, he was the first one to make a dramatically non-mathematical interpretation. They had used them for, they had used the axioms and properties of numbers for differential operators before, but that's kind of analysis and numbers and stuff. And Boole wanted to apply it to classes, and those weren't mathematical objects at all, it was thought. So this was really abstract.
Could you trace what he had available to go on to develop his theories?
Well, he was probably familiar with Peacock's work because he did talk about the symbolical method, symbolical algebra. And although he never cited Peacock, but it's very close to what Peacock was thinking, except broader, in a broader context. So he would have had that. And then there was a development of differential operators in France in the early 1800s, 1815, Savoie, and it lasted for a few years in France. Cauchy, big name, got involved, but even he cited after a while that it wasn't trustworthy, whereas the British mathematicians, a few of them, Gregory and Boole, were very enthusiastic about differential operators. And so Boole had this work with differential operators under his belt to help guide him, as you could have more than just number interpretations.
And still a very big leap to go from there to logic.
It's an enormous leap to go from there and go as far as Boole did. The completeness of his work is amazing.
So few people realize that Boolean algebra is a terminology that came only later, and that his original algebra, Boole's algebra of logic, was different. But how do they differ?
Yes, well, Boole's algebra of logic and the variations that followed were called algebra of logic, not Boolean algebra in the beginning, or sometimes the calculus of classes. Now, Boole's algebra of logic had axioms that looked just like axioms that you use for ordinary numbers, and plus one more axiom, x squared equals x, the idempotent law. His basic operations, two of them, addition and subtraction, were partial operations. Now this can cause a big problem, but it wasn't realized at the time because there weren't many algebras to compare it with. Modern Boolean algebra uses total operations, union, intersection, and complement. And with that, we know how equational logic works. And we still don't have a standard way of dealing with partial algebras.
So what kept Boole from developing the modern calculus of classes based on union, intersection, and complement?
If he had, he would have taken away credit for lots of other people. But he was very attached to the ordinary algebra of the number system, which was the only major algebra that was around. And he was evidently determined to use that algebra as an algebra of logic. And the amazing thing is, he made it work, although people didn't understand why for a long, long time.
So why didn't Boole choose addition to be the union operator for all classes instead of only when the classes were disjoint?
Yes, if he were to define union, the addition operation as union for all classes, then he would destroy his ability to use ordinary algebra, because from that he'd be able to prove that every class was zero if he used ordinary algebra. And he didn't want that, of course.
In what respect did Boole's algebra improve on the long-lived Aristotelian logic of syllogisms?
Yes. Well, the Aristotelian logic handled conversions, which were two-line arguments, and syllogisms were three-line arguments. And what Boole did was to, on the one hand, to liberate the subject and the predicate from being single letters to being complex terms. Instead of saying all A is B, you could say all A or C is B and D. You could make the terms complex. Secondly, this allowed you to put as many terms or classes as you wanted into a proposition. And his next step was, instead of having two premises for a syllogism, he allowed you to have any finite number of premises. So now you had an infinite number of basically categorical type arguments to look at. And the method of Aristotle, which was to make a complete table, clearly wouldn't work. So Boole developed algorithms.
So for the non-technical listener, would it be fair to say that prior to Boole, as of Aristotle's time, people were trying to catalog all possible arguments that people could use in logic,
Yes.
while Boole really made a method to algorithmically compute those arguments, a general method.
Exactly. And the catalog of categorical arguments like syllogisms were very finite, only less than 20. And whereas now Boole was looking at an infinite number, there was no way to make a catalog. So he developed algorithms and based on algebra. And if one knew how to work the algorithms, you didn't have to reason through the exercises. You could just turn the crank and find the answer.
That's a major shift, isn't it, to be able to compute thought?
Computing thought, exactly.
What did Boole mean by a method? He wrote a lot about methods, and what importance did he attach to them in his algebra of logic?
Boole thought that to have a good theory of logic, one needed to have a sense of direction of how to get from the premises to a desired answer. So his method was an algorithm to get from the premises to the desired answer. He called it a sense of direction. And he thought that every good theory should have a sense of direction, even arithmetic. If you're going to add two numbers, you need an algorithm to know how to do it.
What remained to be done to arrive at modern mathematical logic?
Yes, to get to modern mathematical logic, which happened in 1879, 1880 with Frege and Peirce, what one needed to do was to add quantifiers and multivariable relations, not single variable, which would be like a class, a predicate. And with those two steps, and of course finding the rules of inference and the axioms that go with them, this was the big change that developed like first order logic.
So really Frege's work, or?
Well, Frege's work was complete in that sense, whereas Peirce's did not give a complete set of axioms. He did a lot of work manipulating quantifiers, but he didn't have the axioms and the complete list of rules of inference. Whereas Frege, in his work, said, in my work I go beyond Euclid. Euclid gave the axioms for geometry. I give the axioms for logic, but I also give you a complete list of rules of inference. You need nothing more.
How complete was Boole's list of equational laws and rules of inference for his algebra of logic?
Well, Boole's 1854 book was a nice improvement over his 1847 book. The 1847 book only had 3 equations for his laws, and he was up to 7 equations in his 1854 book. But still, he was missing the associative law for addition and multiplication, and he didn't have enough laws for subtraction. But otherwise, he was correct. For his rules of inference, he had equals plus equals give equals, equals minus equals give equals, equals times equals give equals. That was his complete list of rules of inference. He called them axioms of identity, not rules of inference in those days. And what one needs to add are the laws or the rules that govern reflexive, symmetric, and transitive property of equality. And one also needs to use the rule that if n times x equals 0, then x equals 0 when n is 1 or 2 or 3, etc. Because Boole uses that a lot, but he never mentions that as a rule of inference.
Abstraction wasn't exactly the norm yet either in that time.
No, I think Boole was still finding out what all of these things were. He was making progress, but he wasn't at the end yet.
So one thing we haven't broached yet is that there was quite a bit of criticism on Boole's work as well as praise, and some of the criticism pointed actual what would be regarded as blatant errors. For instance, division by 0, which was a very strange thing to do. And it's only later that this got justified somehow. Could you expand a bit on that?
Yes, there was a lot of criticism of Boole's work from the very beginning, starting with Jevons, who regarded Boole's work as dark and mysterious, obscure, and several other adjectives that he used. some of the particular points that they criticized with Boole's use of uninterpretable elements, and that was justified first in 1976, which is a long time, over 100 years after the Laws of Thought was written, by Theodore Halpern from Temple University, using multisets. And another criticism was Boole's work with existential statements, like sum A is B, and Boole represented that using a letter V, VA equals VB. And people didn't believe that you could use equations to handle sum. And so they would derive contradictions from that. It turns out that one of the popular contradictions that was derived was because they didn't read all of Boole's book. Boole did have a habit of adding to his list of restrictions as time went on. So if you didn't read the last chapter on logic, chapter 15, you wouldn't know that you couldn't do the things that they were doing to get their contradiction to Boole, finding fault with Boole. So Boole's work is like a crossword puzzle. You can do a piece of it here, it looks good, and a piece of it there looks good, but when the pieces come together, they don't fit quite, and so you start erasing and going back. That's the way Boole's work is. You've got to know the whole thing and start piecing it together. And with multiple revisions, you can end up with something that makes sense for the whole.
But if it took you 20 years, it's small wonder he was misinterpreted in so many ways.
Yes, I mean, unfortunately, I could not recommend to the average reader to read Boole's book. And as I said before, I really wish that there were a modern version that were as simple looking as Boole's book and yet made things clear. Because if they start reading Boole's book, they will jump to conclusions, and then they have to read the whole thing before making decisions. And who does that nowadays?
What was Boole's rule of 0 and 1, and how did he justify it? And how was his system based on it? On that rule?
Boole's rule of 0 and 1 was stated rather informally, never given a special name. That's one that I've coined, and was not a theorem or such that you could easily refer back to. It was in a certain section in the introduction to his book. And basically it says to see if an argument is correct in logic, all you have to do is take the equations and plug in 0 and 1s for all possible ways, and if it's true, if the argument's good then it's good in logic. And everything in logic can be checked this way, and everything that you check is good in logic. It's an amazing result.
For a computer scientist, it reminds one immediately about what they call the 0-1 principle for sorting networks, where you can verify that a sorting network sorts correctly just by verifying that it sorts all binary sequences of zeros and ones.
Yes.
I wonder if there's a link there.
It could be. I mean, I sort of regard it as 0-1's a test set.
Mm-hmm. Exactly.
It's another way that
Exactly.
it comes up in computer science where they have test sets,
Yes. Yeah. Yeah.
on automata. As Boole's logic was, we tend to think of Boolean algebra in arguments is that you're given some premises and you got a conclusion and you want to check that it's true. And Boole was not so much interested in checking individual ones. He said, give me the premises and I want to draw the best possible conclusion, the strongest conclusion I can. And of course, if you know the strongest conclusion, then from that you can find all the weaker ones. And so he had this sense of, which was not appreciated, I think, that this was his real goal, to get these most general solutions or answers.
Yeah, a lot of these concepts that he introduced were used in so many different fields. It's amazing to look at that, at the scope of the implication. That's sometimes hard to characterize.
That's why I say that if one could write a Boole's book, rewrite it in a comfortable modern language,
Yes.
I think people would realize then just
how much
he did and how much he has, foreseen.
Yeah. Yeah, that includes the use of the uninterpretables as well that he did there, where he made the leap of the imaginary numbers, passing through the imaginary numbers. At least that was his intuition, to get real results, so to speak. Yeah.
His principles of symbolic reason were a bit too general. He said that if you had partial algebras, like you have the reals, but you want to use square root, so you've got a partial algebra because you can't take the square root of -1, and have partial operations. But he said as long as you stuck to the rules, and if you started out with premises that made sense on the rule and the reals, and you went through these complex numbers, which weren't numbers, just symbols, follow the rules, and you end up back in the reals, then the result is correct. This is his principles of symbolic reasoning, and he used the same principles on his logic. He had a partial algebras, and he said, as long as you follow the rules, if you start off with meaningful hypotheses in your partial algebra model, and you end up with a conclusion that's meaningful, then even though you went through things that didn't have much meaning, still, if you follow the rules, it's correct.
And it turned out to be correct.
And it turns out that this was correct in the case he was looking at. There are cases, where it doesn't work, but probably he checked enough examples that he felt very confident that, just that he generalized it a little too much. But then he didn't test it on anything more general, and no one did for a long time. As a matter of fact, I have never seen anyone comment on Boole's principles of symbolic reasoning.
So would I be correct in assuming that Halperin, with his partial algebras or his approach on multisets, signed multisets, basically captured this going through uninterpretables?
Exactly.
And that your part of the work would sort of capture not only the 0-1 principle or the 0-1 rule, as you call it, but also the scope of his logic, which he thought was, which he advocated as a bit too general in retrospect. But
yes, Sanka Panavar, my colleague, Professor Sanka Panavar, he was my first PhD student, by the way, and so we've been friends for a long, long time. He joined me in the last few years to finish up some of the work on Boole that I had been pursuing these many years. And it's always good to have someone to talk to, and Sanka is extremely good to talk to and work with. And so we finished up these questions about, first of all, we point out that the rule of 0-1, what it said. Some people thought that the rule of 0-1 referred to a two-element algebra, but it doesn't. It refers to the integers. The two elements, 0 and 1, are the test elements that you use, but you work in the integers where addition and subtraction, multiplication will all make sense. And so we clarified that and showed that Boole was perfectly right to choose that as a foundation. It works beautifully for everything. And then we turned to the question of how to use this V in the existential statements, the particular statements, sum A is B. And it turns out that Boole gave one approach in his mathematical analysis of logic in 47. And at the end, he makes a comment that his friend, Reverend Graves, whom he had met, I believe, at a recent meeting of the Math Society in Cambridge, had suggested that instead of the translation that Boole used, there should be another translation. Instead of V equals xy, use Vx equals Vy. And translate the universal proposition, all x is y, by x equals Vy, instead of x equals xy. And in the end of Boole's 1847 book, he says that, well, as a matter of fact, I think Professor Graves was correct, that this is the way it should have been done. And afterwards he did it Professor Graves' way. Unfortunately, I wish he hadn't had that suggestion. His first approach was much better, and by just slightly modifying the V equals xy to V equals Vxy, everything works. You can use equations to do particular statements. So even though most people that I've read believe you cannot. The thing is, it's technical in the sense that you cannot translate a particular statement into an equivalent equation, but you can use this translation that I mentioned so that if you have a proof over here in equational logic that ends up giving you a particular answer, it is correct. So it's the whole proof transfers back and forth, not the individual statement. Rather surprising, but which is what you, after all, what you want is to be able to prove things in equational logic. And so you can handle particular statements. So Boole was correct. Just that he got misled, I think. And of course, again, you have to remember that he was a very junior person in mathematics. He didn't have a degree. So he may have felt some need to get along with people who were in places of influence. And of course, it turns out that Professor Graves is one of the people who wrote Boole a very nice recommendation for his job at Cork. So
De Morgan as well? Was he
De Morgan also wrote a very nice letter.
Yeah.
Yes, De Morgan was very fond of Boole and thought it was absolutely amazing that Boole could use the algebra of numbers. Now, De Morgan does seem to have realized that Boole was using the algebra of numbers for the algebra of logic. And I think most people just didn't believe it.
Yeah. Yeah, he made a quite sweeping statement about Boole's impact. Fantastic quote.
Yes, that one would not believe it if you hadn't seen it.
Yeah.
And I think most people today still don't believe it. That's because they haven't had it fully explained to them. Yes, Boole has a problem with uninterpretables, explaining what he means, because he doesn't have the notion of a term, a string. In modern logic, we start off with strings of letters. That's our basic start. And so x plus y looks different from y plus x. The strings are different. Whereas at that time, they didn't have a notion of string. And so there was always a tendency to mix up the semantics of what you thought it meant with the syntax. And so when you take, if you don't have the notion of string, then you take something like x squared minus x equals 0, you can write that as x times x minus 1 equals 0. But x minus 1 is usually not defined. If you had written 1 minus x, it would have been defined. Also true. And so you have equivalent statements. One can be completely meaningful, and the other can have things in it that aren't defined. And you can't separate them unless you speak of strings. If you just speak of the polynomials or their meaning, then they look the same. So what do you mean by being interpretable?
So Schroeder mentions in his Algebra der Logik that the elimination theorem was Boole's main theorem. Would you agree with that?
I think it's his most beautiful theorem, the elimination theorem. I quite agree with Schroeder. Boole emphasized the solution theorem, and I suspect that was because he was tired of the complaints of logicians saying that they could do elimination with syllogisms. And so he put out the solution theorem, which went a step further, and that could not be done with syllogisms. So Schroeder did continue the work on solutions, but that kind of died off as a sort of sideline, whereas the elimination theorem was a mainstream result.
Yeah, what influence did it have on the development of modern logic, that particular theorem?
The elimination theorem spurred a whole industry on decidability. Schroeder tried to improve on Boole's elimination theorem. Boole gave elimination for what we would say existential x of an equation. But Schroeder tried to make that more complicated by having equations and not equations all mixed together and try to eliminate a variable. And that got quite complicated. He didn't really accomplish it. Did it in special cases. And later in 1919, Skolem was able to point out that if one added predicates which count up, which assert that there are at least n elements, then one could do a full elimination. And a sentence then could be eliminated, all the quantifiers could be gotten rid of, and all you would have left would be assertions of the form, there are at least this many elements in the universe, or there are at most this many elements. You would have some Boolean combination of those, and those you can decide if it's true or false.
How did Boole's algebra for secondary propositions differ from modern propositional logic? What was the difference with modern propositional logic?
Yes, Boole took a proposition. We tend to assign it a value, true or false, for, at least for those of us in mathematics, and I think in general propositional logic, you assign a value of true or false. But Boole added the following. He says that, well, a proposition may be true at one time and false at another time. So he added the parameter time in. And so you take a proposition, and it's true for a certain set of times. So he converts the proposition into a set. And this way, he was able to convert sort of propositional logic statements into statements in his logic of classes. They were statements about sets of times. If this set of times is contained in that set of times, then blah, blah, blah. And this was exactly the sort of thing he could handle with his calculus of classes. And whereas later on, people concentrated more on just simply being true or false and working out axioms for those systems.
Could you elaborate a little bit about the notion of time, because it's something that got picked up much later again?
Yes, what Boole did was to look at propositions not simply as true or false, but true sometimes, false other times. Take the proposition, if it is raining, then I will stay home. Well, that's actually two propositions. If it is raining, and I will stay home. So we would say, P implies Q, and true or false values. But Boole would say the times that it is raining are the times that are among the times that I will stay home. And so he would say, let P, little p, say, be the set of times it is raining, and little q the set of times that I will stay home. Then P is contained in Q, and which he would write as P times Q equals P, which is right back into his calculus of classes, because little p and little q are sets of times.
Yeah, a link with temporal logic, perhaps. That came later, yes. Yeah.
So it makes perfectly good sense.
Yeah, pity it was dropped at that time then.
Yes.
Yeah. How did Halperin's book manage to justify much of Boole's work around 1976, 1986?
Yes, Halperin's key idea was actually introduced earlier by Hassler Whitney in 1933, but Whitney didn't realize what he had. Namely, Whitney was looking at characteristic functions for classes. So a characteristic function of a class takes the value 1 on the class, 0 off the class. And Whitney was translating modern Boolean algebra back into Boole's language, essentially. But he didn't realize that. He thought that what he was doing was not really related to what Boole's work was. And what Halperin realized was that the characteristic functions actually form a model that looks just like Boole's. The characteristic functions can be added, subtracted, multiplied, make combinations, and they are isomorphic to the partial algebra that Boole had. But the thing is that the characteristic functions are sitting inside the collection of multisets on the universe U, and the multisets you can add and subtract and multiply them pointwise, and they form a total algebra. And they satisfy all the axioms that Boole was using and all the rules of inference. So the things that were uninterpretable to Boole were no longer characteristic functions, they were multisets. They were perfectly meaningful. And so when you had an argument that started with a statement about characteristic functions that was interpretable in characteristic functions, and you did some equational manipulations that went through multisets and came back down into characteristic functions, then it was a good argument, even though you went through these uninterpretables in Boole's view.
A very computational view, really, to track the multiplicity of the elements like that.
Yes, exactly. And some people sort of, did realize that Boole's work had some sense of counting elements more than once. Mm-hmm. Like if you took A plus B, that could be written as A intersect the complement of B plus twice the intersection of A and B plus 1 times the B and the complement of A. So it looked like the elements of A intersection B were being counted twice. De Morgan made that observation. So in a sense, they were getting the idea, but the algebra of multisets was nowhere in existence at that point. That was a ring that would come much later.
Yes. Was an idea before its time, really.
Yes,
to
yes.
work that out, yeah.
So one could sort of see the idea of what Boole was doing, but they couldn't do anything with it. And they couldn't push it through to see that, yes, the uninterpretable become interpretable.
Like the imaginary numbers. Imaginary numbers was the same situation, really.
Exactly.
Yeah.
I don't think they had the idea, of an embedding, like we, embed Boole's classes as characteristic functions. I don't think they had that notion in the time. So if you don't have isomorphism or embedding,
Exactly.
how do you compare them? Just a different model.
The uninterpretables, basically, with his model, his ring model, but were there other parts that were still left unjustified, that people had doubts about in Boole's work, and that needed to be addressed?
Yes, well, as we mentioned earlier, the question about dealing with particular statements, and Halperin simply brushed that off as unworkable with equations, whereas it is workable. And the rule of 0 and 1, Halperin regarded that as not making very much sense, and simply dismisses it and never goes back to it again. So there were things that needed to be filled out. One more was the fact that, and this is still complicated a bit, is that Boole seemed to be using Aristotelian semantics for his class symbols. That is, he could say from the statement, all A is B, therefore some B is A. He could draw an existential conclusion, which we wouldn't do today, but that was an Aristotelian logic. And Boole did that. And but at other parts of it, so that's not modern semantics for class symbols. And other parts of Boole's work, like his work on the propositional logic, he was quite happy to put x equal to 0, to say x is always false, or x equal to 1, x is always true. So there we see he's not bothered by having things always false or always true, being always non-empty or not equal to the universe. So that part of Boole is one thing that still doesn't quite match up. He seems to be doing one thing over here to make sure that he is able to cover the traditional Aristotelian logic. After all, if he cannot cover Aristotelian logic, he loses a big part of what he claims is great about his system, that he's gone beyond Aristotelian logic. So he covers it, but I think it's something that is not dear to his heart. And in his Laws of Thought, he only devotes one chapter to the treatment of particular propositions. He sends all the previous 14 chapters, he doesn't have any examples at all. So that makes me think that, well, he's trying to push it to the side, but he's got to put it in because he's got to show it's better than Aristotelian logic.
Right.
My thesis has been pretty much that Boole was extremely good at working through examples and finding, sniffing out the good directions, but he didn't have maybe the vocabulary or what to put things precisely. And so I tend to look for what has Boole tapped into that's true. And when he did his rule of 0, 1, well, one only needed to do this for universal existential quasi-identities. But actually it goes through for all Horn sentences. And so Boole was sort of tapping into this result, which was way beyond the language. They had Horn sentences didn't come up until the 1940s. In J.C.C. McKenzie's work, introduced universal Horn sentences. And later on, Horn introduced general Horn sentences, and that's why they're named after Horn, not Mackenzie.
So would you draw the line of where things can be achieved at the Horn level?
Oh, I suspect they can go further. I have actually a fairly simple formulation, but I probably have to write that on the blackboard as to how one can say, well, this is everything you probably would want to look at.
Okay.
You know, and all this would make sense and it all fits in, but you actually need only a small fragment of it to do the results that Boole was doing.
Well, we'll leave that to the enthusiasts to dive into the blackboard recording for later. Thank you.
No matter what that number is, if it's not zero. So why not replace it by 1? Says the same thing. Replace all the non-zero t's